Welcome to this explainer. Today, we're bridging that massive gap between abstract quantum physics and actual practical computer science. We're going to break down the 4 fundamental rules of quantum mechanics and see exactly how they form the ultimate blueprint for quantum computers. If you've ever wondered how these futuristic machines actually process information under the hood, you are in the right place. Let's kick things off with a classic thought from the legendary physicist Richard Feynman. Back in 1981, he hit the nail on the head when he said, "Nature isn't classical, damn it." And he was absolutely right. If we truly want to simulate nature, like complex molecules or intricate chemical reactions, we can't just use standard computers. Simulating nature requires a machine that computes using the very laws of quantum physics itself. So, here's our roadmap for today. We'll start with the classical limit, move into the 4 quantum postulates, explore the quantum circuit model, and wrap up with some concrete quantum gates. All right, part 1, the classical limit. Before we learn the new rules of the game, we gotta talk about why our old deterministic bits hit a literal wall. Think of a classical computer like reading a book, right? You read one page at a time, strictly sequentially. It's deterministic. But a quantum computer leverages a property called superposition, which allows it to act like it's reading all possible copies simultaneously. Because of this, simulating even a relatively small quantum system on a classical computer requires exponential power. Classical machines just run out of memory and time. They simply cannot keep up. Moving on to part 2, the 4 fundamental quantum postulates. Here's the thing you need to remember. Every single quantum circuit ever built relies entirely on these 4 axiomatic rules: state space, unitary evolution, measurement, and composite systems. They are as fundamental to quantum computing as Newton's laws are to classical mechanics. Let's unpack them. Let's look at rule number 1, state space. This essentially defines our game piece. The state of our quantum system is defined mathematically as a unit vector in a complex space, often called a Hilbert space. Now, don't let the math scare you. Unlike a classical bit that is strictly a 0 or a 1, just think of our qubit as pointing to a coordinate on a 3D sphere. This continuous vector space is what allows our qubits to exist in those amazing continuous superpositions. Actually, before we look at how these pieces move, I want to jump straight to rule 4 right now, composite systems, because this is where things get wild. When we combine single qubits, their state spaces don't just add up together. They multiply using something called tensor products. This means the state space scales exponentially to 2 to the power of n dimensions. To really put that mind-bending exponential growth into perspective, if you string together just 300 qubits, you create a computational state space with more dimensions than there are atoms in the observable universe. I mean, think about that for a second. That is the absolute secret engine of quantum computing's power. Classical simulation of something on that scale is simply impossible. Okay, so how do we actually move these pieces? Rule 2, evolution, dictates that an isolated quantum system evolves via unitary transformations. In plain English, it means every operation you apply to a qubit has to be perfectly reversible and preserve all quantum information. There is no delete button in pure quantum evolution. You can always run the math backward to find out exactly where you started. But how do we, actually score? How do we get an answer out of the machine? That brings us to rule 3, measurement. This is the asymmetric one-way bridge back to our classical world. Looking at the qubit irreversibly collapses our beautiful complex superposition into a definite classical 0 or 1 outcome. Once you measure, that quantum magic is just gone. You're left with standard classical information. All right, part 3, the quantum circuit model. What's really fascinating here is how we map those abstract physics rules right onto an implementable computer science framework. When we compare them side by side, classical circuits are kind of like deterministic assembly lines. They use standard bits and irreversible gates, like AND or, that actively waste information. Quantum circuits, on the other hand, are a whole different beast. They use qubits and probabilistic, completely reversible unitary gates. They operate on all those superposed states simultaneously without losing a single drop of data until the very end. So a functional quantum circuit mirrors those physics postulates perfectly in 4 chronological steps. First, we initialize the state space. That's postulate 1. Second, we apply unitary gates to evolve the system. That's postulate 2. Third, we build entanglement between composite systems. Postulate 4. And finally, step 4, we measure the classical output. postulate 3. It is literally physics elegantly translated into software. And that leads us to our final section, part 4, concrete quantum gates. Let's look at the actual physical game pieces, the unitary operators that actually manipulate our qubits. First up is the Pauli X gate. You can basically think of this as the quantum equivalent of a classical NOT gate. Mathematically, it takes your qubit's state vector and rotates it completely upside down. Imagine a globe. The X gate grabs your qubit, sitting at the North Pole, a 0, and flips it straight down to the South Pole, making it a 1. Next, we have the incredibly important Hadamard gate. This one is an absolute game changer because applying this single unitary operator is the spark that kicks off our quantum parallelism. If you feed a definite 0 or a definite 1 into a Hadamard gate, it throws that state into a perfect equal superposition. It places the qubit right on the equator of our geometric sphere, where it is simultaneously 0 and 1. Now, to really take advantage of our composite systems role, we use the 2-qubit CNOT gate. It has a control qubit and a target qubit. When you pair a CNOT gate with a Hadamard gate, something magical happens. You create maximally entangled Bell states. The 2 qubits become so deeply linked that measuring one instantly determines the state of the other, no matter how far apart they are in the universe. Einstein famously called it spooky action at a distance. But for us, we just call it good circuit design. Ultimately, the art of programming this circuit model isn't just about creating random superpositions. If you measure a completely random state, you're just going to get useless noise. The true goal here is arranging these unitary gates to beautifully orchestrate constructive and destructive interference. We want to manipulate the probability distribution so that when we finally pull the trigger and make that irreversible measurement, the mathematically correct answer is overwhelmingly likely to pop out. Which leaves us with a pretty profound reality to ponder as we wrap up this explainer. Breakthrough algorithms, like Shor's algorithm, use these exact rules: superposition, entanglement, unitary evolution, and measurement to factor incredibly large numbers in polynomial time. Since our entire global internet relies on RSA encryption, which assumes factoring those massive numbers is practically impossible, what exactly happens to our digital security when these quantum circuits finally reach their full unbridled scale? That, my friends, is the multi-billion-dollar question. Thanks for tuning in.